I'm going to look at an Atwood machine, but this time the pulley has rotational inertia, and I'm going to say the rotational inertia is going to still be mr squared over 2, and I'm going to use the mass of the pulley as capital M, the radius of the pulley is capital R. So the rotational inertia, mr squared divided by 2. Now, to solve for the acceleration of this Atwood machine, I need to pick a frame of reference like that for the system. The system, I'm going to say moving this way is going to be positive. So positive this way, positive this way. So in other words, the system rotating clockwise, I'm going to call that positive. And I'm declaring that. I know the convention is usually this way. I'm going to declare it to be positive this way. Now, what we have here is 1, 2, 3 different things that accelerate and that have mass. And so we need 3 different force or free body diagrams. So for the pulley, I've got mg down, capital mg down. I've got some support force up. It's probably hanging from something, or it's mounted on something. And I've got 2 tensions. It's really important now that when we're talking about this thing having inertia, these 2 tensions are not the same anymore. When it's massless or frictionless, then all the pulley does is redirect the same force. But if you think of this, if there's friction in here, it has to be friction to make this thing rotate. If there's friction in here, think of if this was an oil drum, right? If I hang a block off here, that block, a rusted oil drum on a rusty rod or something, well, let's just say an oil drum, even if it's frictionless, if I hang something off here, this is going to be so slow to accelerate that this tension is going to be pretty close to mg. Whereas I could hang something off here, this tension is going to be pretty close to that mg if it's barely accelerating. So you can see that those 2 things would be very, very different. It's so hard to move something with a lot of rotational inertia. But right now, that's just to show you that those 2 tensions are different. This doesn't even see these masses. We just want the forces that directly act on the pulley, and there they are. Now, oh, and by the way, I do want to kind of rewrite that. That's my frame of reference. That's my positive direction. Let's look at M1. And I'm just going to put it as M1 rather than a dot. And we've got M1G down, and we've got the tension of this rope, T1, excuse me, over there. Then for M2, we've got the same sort of thing, T2 and M2G. I've got to be really careful about my frame of reference. M1, remember, up is positive. For M2, though, down is positive. And you need that when you write your Newton's second law equations, or you're going to have things in the wrong direction. Let me knock these guys out really fast. Sum of force equals MA. And so T1 minus M1G equals M1 times A. Okay, I'm going to stop right there. Here, M2G, same sum of forces equals MA. M2G is in the positive direction, minus T2 equals M2A. See how those look a little switched? Different tensions. But this is pulling in the positive direction, T2 is pulling in the negative. Tension is pulling in the positive direction, M1G is pulling in the negative. So I've got those 2. Now let's do this one. Sum of torques equals I alpha. And so T2, R times T2 times the sine of 90, because again, we can draw a direct perpendicular line there, R, and I'm going to use that capital R, times T2 times sine of 90, which is 1. That's in the positive direction. This is pulling in the negative direction, so it's minus R times T1 equals mr squared over 2. Remember how we have a problem here? We don't want those 2 things to be different variables. So we'd really like to rewrite this in terms of A, and that is A over R. In this case, that is that R, because A equals R alpha. Okay, it should be a lowercase r there, but in this case, the radius happens to be this uppercase R. Well, look what happens. If I multiply both sides by R, I get R squareds over there. I can cancel out an R squared. Another way is I can cancel those out and then cancel an R out. And so I end up with this. T2 minus T1 equals M over 2 times A. This is what I really like about rotational acceleration, is something elegant that comes out of this. I've got 3 equations, 3 unknowns, oh my gosh. T1, T2, and A. T1, A, T2, A. You can rewrite this T1 in terms of A, and you can rewrite this T2 in terms of A, and you can put them in there. But that's a lot of work. And so I'm going to show you how this comes out really easily. What I'm going to do, I'm going to call this equation 1, equation 2, equation 3, and I'm simply going to take those equations and rewrite them over here. T2 minus T1 equals M over 2 times A. Equation 2, T1 minus M1G equals M1 over A. I'm sorry, times A. And then finally, M2G minus T2 equals M2A. That's equation 2, that's equation 3. If this equals this, and this equals this, and this equals this, then this plus this equals this plus this plus this. Look what happens. T1 negative, I've written this wrong. This is T2 minus T1. Okay, negative T1 plus T1, those cancel. T2 minus T2, those cancel. So adding the rest of it, you get M2G minus M1G equals, and now I've got to erase some stuff here because I need more room, equals, I'll write it like this, M1A plus M2A plus capital M over 2 times A. Well, I can factor out the A and divide both sides, and what you end up with is A equals M2G minus M1G divided by M1 plus M2 plus M over 2. M1 plus M2 plus M over 2. This is kind of neat to me. If you remember when we had Atwood machines with a massless pulley, it looked like that. Because as a system, M2G pulls in the positive direction, M1G pulls in the negative direction. So the net force ends up being M2G minus M1G. And then the only things with mass that had to be accelerated were M1 and M2. Well, now we just have this other thing, and I don't want you to memorize the equation. I want you to be able to derive it, because this may be a pulley with that eye, or it may be a spherical pulley, or it may be something else. It may be a rod that goes end over end. So we don't know what this is generally. We had to actually solve to find that. But here's what I love. You start out 3, Newton's second law, linear, 2 linear ones, 1 rotational. You substitute in. If you substitute A equals R alpha, so alpha is A over R, then all these R's fall out. All these R's cancel. So you notice, even if I had these numbers, I probably wouldn't substitute them in, because it's so nice to have those R's cancel out. It makes the problem a lot easier. Then I'd have 1, 2, and I erase the third equations, put them there. And then when I add them all together, it's really elegant. All this stuff falls out. All the T's go away. It's really nice. And then I end up with I think, a pretty logical result for my A. So that is how we do a 3-body thing. Now, what are some of the variations we could do on that? Instead of having this pulling down, we could have it on a ramp pulling down in that direction. Well, we'd still come down to writing a free body, or writing a Newton's second law for this one, the same Newton's second law that we had already for this one, the same rotational Newton's second law for that one. So even a much more complex problem, almost as hard as I can think of to come up with, is going to have that same structure. 3 Newton's second laws, one of them rotational. Substitute in linear and rotational. Substitute in your A divided by R for your acceleration. A lot of stuff cancels. Then you got 3 equations, 3 unknowns, and here's an easy way to solve them. And solve for A.